Hi everyone, this is Sarfahan. I'm solving paper 5 planning, analysis, and evaluation of May June 2024, variance 52. The duration of this paper is 1 hour 15 minutes. We have approximately 2 questions in this paper and we need to attempt all of them. The total mark for this paper is 30. Let's see what we have in the paper. So calcium carbonate, CaCO3, decomposes when heated as shown. Okay, so that's the thermal decomposition. And thermal decomposition is always endothermic. All right. Which means in order to decompose this compound, energy must be absorbed. The enthalpy change of reaction delta HR for the thermal decomposition of calcium carbonate cannot be measured directly. Okay, that's a very powerful statement. That's a very, very important statement. Why the calcium carbonate thermal decomposition cannot be measured directly? Because it is very difficult to measure, or it is very difficult to know how much energy is absorbed during the reaction. Because it is very difficult to know how much energy is absorbed. Okay. Instead, a procedure involving two experiments is used. And if you are involving two experiments, obviously you are gonna solve this problem via Hess's law. So in order to measure the enthalpy change for this decomposition, I will use the Hess's law. The enthalpy change of a different reaction is determined. And that's what I've told you, that we need to discuss Hess's law in order to find the delta HR, or enthalpy change of reaction for this decomposition. The equation for the reaction in experiment 1 is shown. The enthalpy change for this reaction is delta H1. All right, that's very important. The equation for the reaction in experiment 2 is shown. The enthalpy change in this reaction is delta H2. All right. Now in delta H1, calcium carbonate is reacting with hydrochloric acid, whereas in reaction 2, calcium oxide is reacting with hydrochloric acid. All right. You know that it is a basic oxide, can react with acid to form salt and water. You know, it's an calcium carbonate when treated with hydrochloric acid, you will get salt, water, and carbon dioxide gas. All right. So in experiment 1, weigh a 0.05 moles of sample of powdered calcium carbonate. Why are we using powdered form? To increase the surface area, obviously. To increase the surface area so that rate of reaction increases. Okay. Transfer 50 cm cube in excess of 2 mole per dm cube hydrochloric acid into a small glass beaker. Okay. 2 points here. First of all, how can we measure 50 cm cube? I mean, what sort of apparatus we need to use in order to measure 50 cm cube? By the way, we can use two different apparatuses in order to measure this 50 cm cube. The first one is burette, because burette measures plus minus 0.05 cm cube volume. All right, very accurate, measures very accurate volume. The second one is measuring cylinder. And I've told you in the previous papers, whenever acid is in excess, then we don't need any accuracy in the experiment. And if the experiment doesn't demand any accuracy, we can use measuring cylinder. So I can use either measuring cylinder or burette in order to measure 50 cm. Another very important information is uh, we are placing this amount of HCl into the glass beaker, right? I need to find out the enthalpy change of reaction for this equation, right? And for that, I'm going to use the calorimeter experiment. And in calorimeter, um, I will not going to use glass beaker. Instead, I will use the polystyrene cup, all right, in order to prevent the heat loss. So this might be the source of error. Instead, a polystyrene cup is used. All right. Or what you can do is, in order to prevent heat loss, place the cover on the glass beaker, okay? Start a timer and measure the temperature of the HCl in the beaker every 30 seconds for 2.5 minutes. All right. Okay. After 3 minutes, add the sample of calcium carbonate to the HCl in the beaker. Continue measuring the temperature of the reaction mixture every 30 seconds for a further 5 minutes. Okay. Now, in step 3 and step 4, for both the steps, you need to stir the mixture, all right? So for uniform distribution of heat, so stir the mixture or stir the solution so that all parts of the solution will get uniform heat. All right. And also one more thing. Why are we adding calcium carbonate after 3 minutes? So that the temperature will equilibrate with the room temperature. Okay. Now in experiment 2, repeat experiment 1 using calcium oxide instead of calcium carbonate solid. Part A, suggest why the enthalpy change of reaction for the thermal decomposition of calcium carbonate cannot be measured directly. I've told you about this initially, because it is very difficult to know how much energy is absorbed, because for thermal decomposition, we need more we require more temperature. All right. So because decomposition require heating and it is very difficult to know how much energy is absorbed so it is difficult to measure the temperature. Okay. Calculate the mass in gram of calcium carbonate to be weighed using a 2 decimal place balance in step 1. Okay, first of all, the MR of calcium carbonate we need to find out. We have calcium, we have carbon, we have oxygen. Since we have 3 atoms of oxygen into 3. Calcium has a mass of, I think, 40.1. Let me check out the, let me, um, okay. I need to find out the data booklet first. Yeah, calcium is 40.1. I was right. Calcium is 40.1. Carbon is 12.0. Oxygen is 16.0 times 3. So it's going to be 100.1. Okay. We need to find out the mass of calcium carbonate. So moles of calcium carbonate already given in the question. 0.0500 moles. All right. 0.0500 into 100.1. So I believe the mass of calcium carbonate is going to be 5.01 gram. I hope it makes sense to you. Next, outline how a student should weigh by difference using a weighing board in order to determine the exact mass of calcium carbonate added to HCl in the beaker. Draw a results table with appropriate headings ready for the student to complete. First of all, weigh the mass of weighing board and calcium carbonate. Then transfer calcium carbonate and then reweigh the weighing board. Okay, how can I write the table? First of all, mass of empty weighing board in gram, then mass of mass of weighing board plus calcium carbonate before heating slash gram, then mass of weighing both plus calcium carbonate after heating, and then mass of calcium carbonate. Okay, so this is the table. Identify which piece of apparatus should be used to measure the volume of HCl in step 2 and give a reason for your choice. Uh, if I'm using burette, I'm going to write it. It has an accuracy of plus 0.05 cm cube volume. If I'm going to write measuring cylinder, obviously I'm going to say that hydrochloric acid has to be in excess, so we can use measuring cylinder. So I can write both, right? It depends on me, actually. So can use burette because it measures volume accuracy to plus minus 0.05 cm cube, or can use measuring cylinder because HCl is in excess. Without making any changes to the apparatus, suggest an instruction to be added to step 3 and step 4 to make experiment more accurate. For accuracy of the experiment, step 3 and step 4, we need to stir the solution so that all parts of the solution will get uniform heat. So stir the solution. So that all parts of the solution will get uniform heat. Part E. A student carries out experiment 1 and obtain the results given in table 1.1. Okay. Plot a graph on the grid in figure 1.1 to show the relationship between temperature and time. Use a cross X to plot each data point. Okay. So we have a relationship between temperature and time. Temperature has to be on the uh, temperature has to be on the y-axis, which means it is a dependent variable, and time has to be on the x-axis, which means it is independent variable, right? The points and lines of best fit for the data before 3 minutes have been drawn for you. And why it is constant so that it will equilibrate with the room temperature. All right. Draw a line of best fit for the data after 3 minutes that will enable you to determine the theoretical temperature increase at 3 minutes. Okay. So I have to plot the points. So at 3, there is no point given, but 3.5, we have 27.5. 3.5, we have 27.5. 3.5 is here. 25, 26, 27, 27.5. Okay, somewhere around here. Somewhere around here. Okay, now the next is at 436, at 436, 4, 30, 35, and this one is 36. Okay, then 4.5, 34.5, 4.5, 4.5, 34.5, 34, 34, 4.5, 34.5. So this is 31, 32, 33, 34, and 34.5. Okay. Then 5, 32.5, 32.5, 30, 31, 32, 31, 32, 32.5. Then 5.5, 32. Then 5.5, 32, 30, 31, 32, 30, 31, 32. Okay. Then we have at 6:31, at 6:31, like here. Then we have 6.529, 6.529, somewhere here. 26, 27, 28, 29. Okay, it has to be here. Okay. Then we have 728, 728, 25, 26, 27, 28, 725, 25, 26, 27, 28. Okay. Then we have 7.5, 26, 7.5, 26, 25, 26. And then at 8, we have 25.5, 25.5, 25.5. Okay. So basically, this is 27, 26, 27, 28, 29, and this one is 30. Okay. And this is 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8, 2.9, 3. Okay, I hope it makes sense to you. Let me check at 0.5 and 5.5. At 5, 32.5, 32.5, 31, 32, 32.5. Okay. My mistake has to be here. Okay. And at 5.5, 32, 5.5, 32, 30, 31, and 32. It's fine. Okay, it's fine. Let me draw the line of best fit. At 8. It has to be like this. And I need to extrapolate it. I need to check these 2 points also. 6.5 we have 29. 6.5 we have 29, 25, 26, 27, 28, 29. That's right. That's right. And at 7, 28, 25, 26, 27, 28. That's also right. And at 7.5, 26, 25, 26. That's right. Oh, so might be I have, that's the only point. Okay. And we need to extrapolate it like this. So how much temperature we have received from here? So it's basically 35, 36, 37, 38, 38.5. It has to be, wait, let me check my, no, it's not. Okay, it's fine then. And how much time is 19? 19. I bet 19.0. Okay. 19.0. 38.5. 39 and then 40. Yeah, it's fine. Let me check my graph again because I'm a little bit need to think about this. This is at 6:31. 31, 30. Yeah, it's fine. 25, 26, 27, 28, 29. It's fine. It's fine. That's fine. So there's a graph actually. Now the next part is use your graph to determine the theoretical temperature increase at 3 minutes. So at 3 minutes, we have 38.5 minus 19.0. So 38.5 minus 19.0 is going to be 19.5. So 19.5 degrees Celsius is my answer, okay? Let's move on to the next part. Suggest why the temperature measured at 3.5 minutes is lower than the temperature measured at 4 minutes. If the temperature was lower than at 4 minutes, then it means calcium carbonate has not reacted fully with hydrochloric acid. So calcium carbonate did not fully react with hydrochloric acid. Okay, that's the temperature examiner is talking about. Lower and then higher. A student carries out experiment 2 and determine a temperature increase at 62 degrees Celsius. That's very, very important. The heat released, which means reaction is exothermic, by the reaction Q is given by this expression. We have done it in A1, where M is the mass of HCl and the mass of HCl was 50 cm cube initially. That is the mass of HCl. Okay. Assume that 1 cm cube of HCl has a mass of 1 gram, and that the specific heat capacity of the solution is 4.18. Calculate Q in joules for experiment 2, and hence determine delta H2 in kilojoules per mole. So yes, I can calculate the value Q equals to mc delta T. M was 50, the specific heat capacity is 4.18, and temperature change is also given, which is 62.0. So Q is going to be 50 into 62 into 4.18. So it's basically 12,958 joules, right? So Q is 12,958 joules. In order to calculate delta H2, I will use the moles. And moles was given initially 0.0500, if you remember. These are the moles. Okay. So when we have this much moles, energy released is 12,958 joules. If we have 1 mole, so divided by 0.05, it's basically 259.160 joules converted into kilojoules. So divide by 1000. So it's basically 259.16 kilojoules. So 259.16 kilojoules. And since heat is released, which means sign has to be negative here. Okay. Use the energy cycle below, and this energy cycle is called thermochemical Hausdorff cycle. Use your answer to G, this answer, and the information given to determine delta H1 for the thermal decomposition of calcium carbonate. Remember, enthalpy change for experiment 1 is also given, which is minus 84. So I need to find out the standard enthalpy change of reaction for this equation. This is going to be delta H1, and its energy is minus 84. This is delta H2, and its energy I have calculated in part G, which is minus 259.16. So what I can do is I need to make an arrow in the clockwise direction. Obviously, this value is going to be positive because it matches with the clockwise rotation. This value is also going to be positive because it matches with the clockwise rotation. So minus 259.16. This value is going to be negative because it not matches with the clockwise direction. So it's minus 84 equals to 0. Then delta HR, enthalpy change of reaction, is minus 259.16 plus 84 equals to 0. Then the standard enthalpy change of reaction, I believe, is going to be how much? Let me calculate. It's basically plus 175.16 kilojoules per mole. That's my answer, plus 175.16. Let me recheck my calculation again. 259.16 minus 84. Yes, 175.16. When it will turn, yeah, plus, it's minus, and then right hand side positive. Okay. Part I. Last part of the question, identify the main weakness of the experimental procedure and suggest one improvement to overcome this weakness. The main weakness is not the type of thermometer used. Main weakness. Oh, that was the main weakness. I've told you. That is the source of error. We were using glass beaker. Instead, we need to use polystyrene cup or place a cover lid on the glass beaker to prevent heat loss. Either you need to write the first one or the second one. It's totally up to you. I mean, examiner give marks on both the reasons. So I'm going to write both. Main weakness, heat loss from the top. Improvement, use cover lid. Okay. Use cover lid. Second reason, use polystyrene cup. Reason, oh, not the polystyrene cup. Uses glass beaker. So improvement should be use polystyrene cup. Okay. So that's the end of question number 1. I hope it makes sense to you. All right, let's start question number 2 of June 2024, variance 52. This question is about an experiment to investigate the effect of temperature on equilibrium constant K1. So according to A1 chemistry, equilibrium constant depends on temperature. So if temperature changes, equilibrium constant changes. If temperature constant, equilibrium constant remains constant. Okay. So the reaction is given in the question. The data collected is used to determine the value of the enthalpy change of the reaction. To set up the equilibrium, aqueous iron 3 nitrate is mixed with aqueous potassium thiocyanate. Aqueous iron thiocyanate forms which have a red color. So you need to remember the red color of this complex, okay? A calorimeter is used to measure the absorbance of the reaction mixture. That's a very straightforward information. A calibration graph can then be used to determine the concentration of this ion in the reaction mixture. Table 2.1 shows the solution for the experiment. So as you can see, concentration increases. Okay. Concentration increases. Okay. Now, in the first part of the question, describe how you would prepare 100 cm cube of solution B from solution A, which means I need to prepare this solution into B. Okay. So the concentration of solution B is C1. The volume of solution B is V1. The concentration of solution A is C2. And volume, I need to find out. Okay. Include a calculation of the volume of a solution A required for the preparation of solution B. Give the name and capacity of any key apparatus that should be used. Write your answer as a series of number discussed. So first of all, let me write the calculation first. For dilution, I'm going to use C1 equals to C2 V2. The C1 is 0.00200, volume is 100 cm cube. The concentration for C2 is 0.00920 and volume needs to be determined. So volume is going to be 21.74 cm cube. And I know that this volume can only be measured through burette. All right. So let me write the second point. Use 50 cm cube burette. to measure 21.74 cm cube of 0.00920 mole per dm cube. Mole per dm cube is also called molar. Mole per dm cube solution and transfer it into a 100 cm cube volumetric flask. Top of the solution with distilled water. Distilled water dropwise. Until mark is reached. Stopper the flask and mix well. Okay. Next, before starting the experiment, solution B and D are used to produce calibration graph. Known volumes of each solution are added together and the absorbance for each mixture is recorded. The calibration graph is shown in figure 2.1. The concentration of solution D is much greater than the concentration of solution B. In order that solution D is in excess, suggest a reason why solution D is in excess. Okay, the concentration of solution D is much greater. Okay, see, if we increase the concentration of this ions, equilibrium favors towards right hand side. And if equilibrium favors towards right hand side, then this increases the concentration of iron thiocyanate ions. Okay, that's the whole logic behind that concentration. So let me write it here. Increasing concentration favors equilibrium towards right hand side. This increases the concentration of Fe SCN 2 plus ion. Okay, now the y-axis is the relative absorbance, which means it must be the dependent variable, whereas concentration of iron thiocyanate ion is the independent variable. Graph is already given. Let's see what we need to find out from this graph. Oh, part C. The following experimental procedure is used. Half fill a large beaker with water at room temperature, that is 25 degrees Celsius. Transfer about 40 cm cube of solution B into the boiling tube and place the boiling tube in the beaker of water. Okay. Transfer 5 cm cube of solution C into the test tube and place the test tube in the beaker of water. Wait for 10 minutes. Transfer 5 cm cube of solution B from the boiling tube to the test tube containing solution C. Stir the mixture in the test tube and record the temperature of the mixture. So we need to stir the mixture for uniform distribution of heat, for uniform heating. Okay. Measure the absorbance. If I'm measuring the absorbance, obviously it's going to be the dependent variable, because what we measure is the dependent variable. What we measure. Okay. Change the temperature of the water in the beaker and repeat step 3 and 6 for different temperature. Change the temperature is basically your independent variable, because what we change is independent variable. Identify the dependent variable. Obviously, absorbance. Describe how you would adjust the temperature of the water in the large beaker to obtain a temperature of 10 degrees Celsius. There are two ways to maintain the temperature. The first one is quenching with ice, or the second other option is thermostatically controlled water bath can be used. So thermostatically controlled water bath can be used to measure the temperature or to maintain the temperature, or quenching process with ice. A student obtained the results given in table 2.2. Okay, this is the temperature, this is the relative abundance, relative absorbance, this is concentration of iron thiocyanate, and this is K1. The value of the equilibrium constant K1 can be determined using equation 1. So I need to find out the value of K1 by using this expression. And this expression, X is the concentration of iron thiocyanate in mole per dm cube. Use the calibration graph in figure 2.1 to complete the column 3 in table 2.2. Record the values to one decimal place. That's another very, very important aspect, that we need to record the values up to one decimal place. Use equation 1 to complete column 4 in table 2.4. Record your values to the nearest whole number. Okay. So at 0.6 absorbance, the concentration of iron thiocyanate ion must be at 0.6. At 0.6, this is 0.6. Okay. So at 0.6, it's going to be how much? 8.1, 0.2, 0.3, 8.4, 5, 6, 7, 8, 9, 10, 8.4. Okay, mole per dm cube. So first is 8.4. And let me put the value of 0.84 here and get the answer. It's K1 equals to hold on, 8.4. So K1 equals to 8.4 divided by 0.0010 minus 8.4 whole square. So hold on a second, please. 0.0010 minus 8.4, and that is square. 8.4 divided by this. So it's 0.119. I think that's the value, 0.119. Let me check. No. I made a mistake, I think. The value of x is 8.4. 0010 minus 8.4. Hold on. 0.0010 minus 8.4. Divided by answer. Okay. So the value here is going to be 1.90. So that's going to be 107, I believe. Okay. So when the absorbance was 0.42, let me take out the concentration of FeSCN. 0.42, 0.42, 0.42 absorbance, 0.4, 1, 2, 3, 4, 5, 6, 7, 8, 9, this 0.42, this one. And its absorbance value is 6.123, 6.2, I believe. Yeah, 6.2 molar per mole per dm. So this is 6.2. If I'll use this value and, plug in the values and get another answer, let me take out the answer. It's going to be 70. Okay. So this must be the one decimal place, and this must be the whole nearest whole number, nearest whole number. Okay. Next, another student does the same experiment for 7 different temperatures, plot a graph, and draw the line of best fit as shown in figure 2.2. All right. The theory predicts that the relationship between K1 and T is given by the equation 2, and that equation is y equals to mx plus c. All right. You can apply this linear equation on this expression. Delta H is enthalpy change of reaction and T is the temperature in Kelvin. Explain why the graph supports the relationship between K1 and temperature given in equation 2. That's very, very important. This log K1 has the relationship with temperature. Okay. So there is a straight line graph indicate that both log 1 and 1 over t are proportional to each other. The straight line graph supports that log K1 and 1 over t are proportional to each other. Okay. Circle the point on the graph in figure 2.2 that you consider to be most anomalous. So most anomalous point must be this one. Okay. There were no errors in the measurements in the experiment. A student correctly suggests that the anomaly was caused because the absorbance was lower than expected by the line of best fit. Okay. Suggest why the absorbance was lower than expected. So absorbance was lower than expected. If absorbance was lower than expected, okay. If absorbance was lower than expected, then the actual temperature was higher than expected. Because if temperature increases, absorbance decreases, right? So if absorbance decreases, then it means the temperature measured was higher than expected. And therefore, if temperature was higher than expected, this will lead to the lower concentration of iron thiocyanate. Oh, that's the relationship here. See, absorbance decreases as temperature rises. Concentration of iron thiocyanate decreases. So between these lines, I need to write my explanation here. As absorbance was lower than expected, then it means the actual temperature was higher than expected. This will lead to the lower concentration of iron thiocyanate ions. Determine the gradient of the line of best fit in figure 2.2. State the coordinates of both points you use in your calculation. There must be selected from the line of best fit. Give gradient to 3 significant figures. So gradient has to be in 3 significant figures. Okay. And we need to find out the gradient from the line of best fit. Okay. So from the line of best fit, let me take out the first 1, 2, 3, 4. Let me take out this value. Okay. So this must be 1.84. Okay. and this must be 0.0035306. 0.00306. Okay. And the end point we could take is let me take this point. Okay. This is going to be 2.13. And this is going to be 0.00356. Okay. So let me write both the gradients. 0.00306 and then 1.84. Coordinate 2 is 0.00356 and 2.13. The gradient is going to be 2.13 minus 1.84 divided by 0.00356 minus 0.00306. So gradient is going to be 580. Oh, no, not 580. Let me check. 2.13 minus 1.84. 2.13 minus 1.84. So its value is 0.29. 0.00356 minus 0.00306. It's basically 5 into 10 to the power minus 4. So 0.29 divided by answer. It's 580 exactly. Okay. Gradient is 580. Use the gradient calculate in E part 3 and equation 2 to calculate the value of the enthalpy change of reaction delta H. So this must be your y-axis. This must be your C, y-intercept. This must be your gradient. And 1 over T is basically your x-axis. Okay. So gradient is basically minus delta H upon 2.303 R. Gradient was 580. I need to find out the delta H over 2.303. The value of R is constant. It is gas constant, which is 8.31. So delta H is going to be minus 11099.999 joule per mole. So if I'll convert it into kilojoule, it's going to be minus 11.1 kilojoules per mole. So it's going to be minus 11.1 kilojoules per mole. I hope it makes sense to you. That's based on calculation, mostly calculation, right? Thank you very much, guys.